Okay, so let's look real quickly at the derivative of a base other than e. But all of this is predicated on the fact that the derivative of e to the x is indeed simply itself. Now, one of the things that we'll have to know in order to get the derivative of a to the x, and this right here, don't worry about this so much, but this is the definition of an exponential. A has to be a positive value, and a can't be 1 in order for this to all work out. But we have to know that if you do a to the log base a of x, remember a logarithm and its common base is the same base. They basically are inverses of each other, so this just comes out to be, okay, so again, we have to know that a to the log base a of x just cancels out and just gives you x. Okay, so instead of us using the limit definition, we can actually just use the chain rule here. So we're going to start with y equals a to the x, and we're going to find the derivative of a to the x. And so like I said, what we want to do is rewrite this in terms of e to the x, and so we're going to use the fact that a to the log base a of x is just x. Okay, so we're going to rewrite this as e to the natural log of a to the x. Okay. So that is the same as this. Now, why can we do that? Well, it's because e and the natural log are the same base. So they would cancel each other out, and you would just get a to the x. This comes out to be the exact same thing. Now, why do we do that? It's because we know how to find the derivative of e. Let's go ahead and bring that x down to make this a little bit nicer. Because remember, that's a rule for logarithms. You can bring the exponential. If you have log base a of, I don't know, b to the x, for instance. It makes it x log base a of b. Okay? And so this would be e to the x, natural log of a. Now we're going to do our chain rule here. This is like your u here. So we'll end up with e to the u times u prime. So the derivative would just be e to the x, natural log of a. That part didn't change. Now we have to find the derivative of x, natural log of a. Well, natural log of a is just a number. And so if you take the derivative of x times the natural log of a, the derivative of x is just 1, and times the coefficient would just be natural log of a. Okay. Now, show you where to go next. Let's rewrite this again. Remember, that's the same as the natural log of a to the x, so just bringing that exponent back up. And e and natural log cancel out, and you're just left with a to the x times natural log of a. So essentially, if you take the derivative of some number to the x, okay, it's the same as, you get the exact same derivative, a to the x, but then you have to multiply by the natural log of a. Okay, it's super commonly forgotten to drop that natural log, but don't, okay? This actually ends up working out if you did the same thing. What if it was e to the x and you used the same rule? It would be e to the x times the natural log of e, and remember that's just 1. Okay, so it's always kind of in there. All right, so if it was the chain rule, use the same thing again, be a to the u times the natural log of a, but then you'd have to multiply by u prime. So just keep that in mind. Let's do a couple examples. F of x equals 6 to the x. Okay, so remember, an exponential means that basically you have an exponent with a variable in it. Okay, and so we're just going to keep in mind our derivative of a to the x is itself and then times the natural log of a. So f prime of x would be 6 to the x and then times natural log of 6. That's it. Okay. Over here, we're going to have to use the chain rule. So this is 3 to the u. Okay, so we're going to do f prime of x would be, keep it exactly the same, and then times the natural log of 3. Okay, so here's our just e to the, or 3 to the u part, derivative of that. But now we're going to have to multiply by the derivative of 6x, which is just 6. Now note the derivative of 4 is 0, so that sucker goes away. Now, the coefficient of this is actually 6 natural log of 3. This component right here makes up the whole coefficient of 3 to the 6x. Okay, ugh, icky. Okay, but think of it as 8 to the u. So if we took the derivative of that, it would be 8 to the u times the natural log of 8 and then times u prime. All right, we can do that. So f prime of x, like I just said, would be 8 to the u, which is x squared minus cosine x, times the natural log of 8, and now times the derivative of x squared cosine x minus cosine x, which would be 2x. Remember, the derivative of cosine is negative sine, so this would become now a positive sine x. Not pretty, but it's not the worst thing that could ever happen. All right, f of x equals negative 2 times 3 to the x all divided by e to the x. We've got some options here. You can do the quotient rule, or you can rewrite it, which is what I'm going to do. The negative 2 is simply a coefficient of everything else, and this is times e to the negative x. Okay, so I am going to use the product rule. This is going to be my f, and that sucker is going to be my g. Note that you are going to have to do the chain rule inside of this, so think of it as e to the u. So we do f prime g plus g prime f, the derivative of f, okay, would be negative 2 is just chilling there, times, stays the same, times natural log of 3. Okay, and then times, so here's your f prime, g, which is just e to the negative x, plus, now we got to do our g prime. Okay, so the derivative of e to the negative x is e to the negative x times the derivative of negative x, so you've got to use the chain rule, which is negative 1. I'm going to clean this up in just a second. So here's your g prime. Now I got to multiply it by f, which was negative 2 times 3 to the x. So just to make this sucker look a little bit nicer, this would be negative 2 natural log of 3 times 3 to the x times e to the negative x. Over here, this negative 1 times negative 2 becomes a positive 2 times 3 to the x times e to the negative x. And you'll see this, well, this is 100% correct. You'll often see it written with these crazy stuffs, this 3x e to the negative x factored out. So you can actually factor out the 2 times the 3x times the e to the negative x, and you'd be left with a negative natural log of 3 plus 1. Which is kind of interesting, right? 1 minus natural log of 3. This does look much cleaner. Okay, let's do this one real quick. If f of x equals x squared sine x, what's the equation of the tangent line at x equals pi? Okay, so that of course means we're going to need to take the derivative. And think of this as your e to the u again. So be u prime e to the u by chain rule. So our derivative, we don't have enough room. Our derivative would be e to the x squared sine x, and then times the derivative of this. Now, oh my gosh, we're going to have to take the derivative of x squared sine x, which means we're going to have to use the product rule. Okay, the derivative of x squared would be 2x, and then times sine x, plus the derivative of sine x, which is cosine x, and then times x squared. Okay, so that's times all of this lovely guy. Oops, it's x squared cosine x. Okay, and while there's nothing really we can do to simplify that, we are going to need to find f prime of pi now in order to know the slope at pi. So let's see this. This is e to the pi squared times sine of pi times 2 pi sine pi plus pi squared cosine pi. You're going to have to wait. Okay. All right. So remember, pi is over here, and its point is negative 1, 0. Okay. So the cosine of pi is negative 1, where the sine of pi is 0. So this ends up with e to the 0 times this sucker 0. This will be pi squared times negative 1, so basically negative pi squared. So e to the 0 is just 1. You have 1 times negative pi squared. Our slope is negative pi squared. Okay, so our slope is negative pi squared. We are missing the value, the y value at pi, though. So let's find f of pi. Plugging it back up into our original equation would be e to the pi squared times sine of pi. Remember, sine of pi is simply 0, so we have e to the 0, which is 1. So we have a point, pi comma 1, and we have the slope, it's negative pi squared. We're going to do y minus y1. It's negative pi squared times x minus pi. Okay, icky, but not too bad. So let's do another example. At what point, or points, is the tangent line of f of x equal e to the 2x plus 3 parallel to y equals 7 plus 2x? So remember, this is going to give us a slope of 2. We're going to find the derivative and set it equal to 2, basically. Make sure you're using the chain rule. So, which says I'm going to keep its own derivative. Remember, it's just the same. And then times the derivative of 2x plus 3, which is just 2. Now, this is great, but I'm looking for the value of x. That will give me a slope of 2. So let's set this equal to 2. Dividing both sides by 2 will leave me with e to the 2x plus 3 equals 1. Okay. So remember, we're going to change this to the logarithm and take the natural log of both sides. And the reason why that would be awesome is because, remember, the natural log of e, natural log is, or does have, base e, so they would cancel, and you would get the natural log of e would just be 1, and then to the 2x plus 3, the exponent would just be the answer, and the natural log of 1. Well, if you don't remember, log base a of 1 is always 0, because what you're looking for in a logarithm is a raised to the what gives you this number here, the input value. So a to the 0 is 1. So regardless of what the base is, if you're doing the log of 1, log of anything, a log base anything of 1 is always 0. And solving that, we get x equals negative 3/2. Okay. Now, this just gives us our x value. If we do indeed need to find our y value, because it says at what point, we plug negative 3/2 back in. It'd be e to the 2 times negative 3/2 plus 3. So this would be e to the negative 3 plus 3 is e to the 0 is 1. So our point would be negative 3/2 comma 1. It just depends on, are you only looking for the x value or looking for the overall point. Continuing on with our examples here. Oh, we've got an exponential within an exponential. Fine. Take the derivative of both of these. We're going to use the chain rule here, and then separately a chain rule there. So we have e to the 2x, and then times 2. I'm hoping that this, you're picking up on this pretty quickly. E to the u is just e to the u, and then times u prime. Okay. Now over here, remember the derivative of a to the x is a to the x, and then times the natural log of a. We've got a u here, so we're going to have to do that. The derivative of 2e to the x, the derivative of 2 to the u, for instance, would be 2. Keep it exactly the same, then times the natural log of 2. And now we're going to have to take the derivative of e to the x, which magically is e to the x, which is what everything is predicated on. All right, on the next one, I want you to try and work this one out on your own. And then come back to it and see if you get the right answer. And if you need help, then you can follow through or fast forward to the next part. It's fine. Okay. But I'm going to assume that you've now worked it out. And if you've done it correctly, you get the natural log of 5. Working that one out. So let's think of this. This is e to the negative 3x. Otherwise, you got to use the quotient rule. Taking the derivative would be e to the negative 3x and then times negative 3. Now the slope of this sucker is negative 5. You can simply solve it and get a negative 5. So we're going to set this one equal to negative 5. Dividing by 3, you'll get e to the negative 3x equals positive 5/3. And just like on the last one, we're going to take the natural log of both sides. And you'll get the natural log of e to the negative 3x equals the natural log of 5/3. But by doing that, the natural log here cancels, and you get negative 3x equals the natural log of 5/3. And as I said, you get x equals the natural log of 5/3, all divided by negative 3. Yay! Okay. All right. Next one, like I said, feel free to try this one on your own. We're going to take the derivative and basically set it equal to 0 because it says, where does it have a horizontal tangent? Okay. Now, just so you know, e to the x will never have a horizontal tangent. As it approaches negative infinity, it will approach 0. But when we minus the 2x, that introduces the additional component where it might indeed change direction at some point. So let's, of course, take the derivative, make it e to the x minus 2. Set it equal to 0. This should be a pretty simple one. When x is the natural log of 2. Okay, I just took the logarithm of both sides, and there we go. Okay, next one, find the 1,000th derivative of f of x equals x times e to the negative x. Again, try this one on your own. And let's see how. Okay, again, try this one on your own, see what you get, and come back. And you should get that the 1,000th derivative is e to the negative x times x minus 1,000, or the equivalent thereof. And if you're like, what? How'd you get that? Again, remember, we're going to look for a pattern. First derivative, we're going to use the product rule here. There's your f, there's your g. Got to use the chain rule on the second part. Derivative of x is just 1. And then so times e to the negative x plus derivative of e to the negative x is a negative 1. E to the negative x, and then times x. So notice, of course, we can factor out e to the negative x, and we're left with 1 minus x. Similar to one we did before. Let's see what happens with our second derivative. Okay, so I'm going to use the unfactored form to do that. Derivative of e to the negative x is negative e to the negative x. Now, notice this is the opposite of what we originally took the derivative of, okay? And so if I took the derivative of this again, it would be this entire function right here, just the opposite sign. So it should be minus e to the negative x, and then plus x e to the negative x. We end up with 2 of these e to the negative x's. It's just the sign is different from the last problem. By factoring out an e to the negative x, you should see you end up with e to the negative x times x minus 2. So notice what happened in the first derivative is a 1 minus x, and the second derivative is x minus 2, the opposite sign. Let's see if that's indeed true for the third derivative, and you can check this for the fourth as well. On our third derivative, we're going to take the derivative of negative 2e to the negative x, and that's just a positive 2e to the negative x because of the negative sign here. And then the derivative of x e to the negative x is all that right there. So it is plus e to the negative x, and then minus x e to the negative x. We have 3 of these e to the negative x's, minus x e to the negative x, factor out the e to the negative x, and you can see it's 3 minus x. So what appears to be happening is if it's odd, the sign is negative, and this is replaced. Okay, so if we can think of an odd derivative, would end up with n minus x. An even derivative would end up with n plus x. Okay, or x, excuse me, minus n. Okay, and so since f to the 1,000 is even, it's going to be x minus 1,000, and then times e to the negative x. All right, last one. If you really want to do number 19, you can, but we're going to go over how to use your calculator to solve these functions and do all this fancy stuff. Okay, this right here is called a differential equation, which might be one of my favorite applications of all of calculus. I mean, it is just straight up awesome. It's the best thing you could ever possibly do algebraic-wise, and it's got tons and tons of uses. And what it's doing is it's relating an original function to its derivatives. Okay, so this is saying find the values of r such that, and this should really say, oops, excuse me, a 0 right there, excuse me. 0 equals y triple prime minus 4y prime minus 5y. Okay, and I believe on your paper it's got a 0 as well. All right, so we're going to evaluate. We're going to try and find the values of r that make this lovely guy true. Okay. All right, so basically you're going to substitute in y. You're going to substitute in y prime, and you're going to substitute in y double prime. Or, whatever I said. Okay. So basically we're going to substitute in y prime, we're going to substitute in y, and we're going to substitute in y double prime here. Okay. So let's go ahead and find y prime. Using the chain rule, this would be r e to the rx. The second derivative, r is just a constant. So if I multiply by another r, it would be r squared e to the rx. Okay. And y is, of course, just y equals e to the rx. So let's see what we got here. Y double prime minus 4y prime minus 5y. Y double prime is r squared e to the rx. Okay. Minus 4y prime, so minus 4 r e to the rx, and then minus 5y, which is r e to the rx. All right, so let's factor out an e to the rx because it's just in our way, and we're left with r squared minus 4r minus 5. Oops, there's an extra r there. Okay, now an exponential can never be 0. So we're not concerned with that part. That part can never be 0. We're concerned with r squared minus 4r minus 5 equals 0. Now, we can factor, use quadratic formula, whatever. But you end up with r minus 5 times r plus 1. So r equals 5 and r equals negative 1. Essentially what we're saying, if we have these two equations, e to the 5x, or e to the negative x, they satisfy that if I took the second derivative minus 4 times the derivative minus 5 times the original function, it would equal 0. And the same thing with this one. Okay, which is kind of cool. So here are two values of r that satisfy this. Now your homework, and it's due on Monday, is to do the WebAssign on exponential functions, the derivatives of exponential functions. If you need any help, just ask, but you have all weekend to do it, and you have in class on the half day on Thursday. And that's it.